we will start with the topic of potential energy. In the last lecture, we were talking about the work energy theorem. The statement for that work energy theorem says that the net work done by the total force acting on the particle is equal to the change in particle's kinetic energy. Okay, let's use this knowledge that we have and apply it to a real problem. And this is an example in which you have a television tube, you have a cathode, and you have an anode, and the cathode is basically giving up electrons, and these electrons are getting accelerated because there is a potential difference between the cathode and the anode. That is, you have these deflecting coils which can take these electrons and they can project them anywhere on the screen. Okay, so the question that we want to answer is that this electron that is accelerated, it is getting accelerated from a position of rest to a value of energy of 2.5 kilo electron volts. Okay, and the distance that it is getting accelerated over is 50 centimeters. And the reason why it is being accelerated is there is a electric force because of the electric field that is present inside the tube. So we want to find the force in newtons on the electron, and we will assume that the force be constant and the force is in the direction of motion so that it can get simplified. So we know the work energy theorem is net work done is your change in kinetic energy, okay, which is nothing but the kinetic energy final minus kinetic energy initial. All right, so in our situation it is starting from rest, so the kinetic energy initial will be 0, right, because it is starting from rest. Velocity at rest will be 0. So all we care about is the final kinetic energy, and the final kinetic energy is given, it is given as 2.5 kilo electron volt. Okay, now work done is force times displacement. Okay, so the force that is acting on the electron is what we need to calculate. The displacement is given as 50 centimeters. So in Newton and in SI units, that would be 0.5 meters, and this is equal to your 2.5 kilo electron volt, right? So if I change this kilo electron volt in Newton units, that means I will have to change it to your coulomb. So let's do that. Take 2.5, and 1 electron volt is 1.6 into 10 to the power minus 19. That is what you get, and then you divide it by your 0.5. Okay, and there will be a factor of 1000. There is a 0.5 here, so it will be 25 divided by 5, or it will just be 5.0 actually, right? You have 5 into 1.6. So 10 to the power minus 19 into 10 to the power 3, you get 10 to the power minus 16, that is newtons, and 5 into 1.6, it is 5, 6 are 30, so it is 8 into 10 to the power minus 16 newtons. So change everything to meters, kilograms, and second, and then in the end, always you will end up with the SI unit. Okay, the final answer will always be in newtons. That was about the relationship between work and kinetic energy. Okay, so let's consider the case of a spring. All right, and in this spring, we are basically compressing the spring by applying some force F1 and F2, and these are equal and opposite forces. Okay, so what will happen is this spring will get compressed, and in both the cases what is happening is you have equal and opposite forces acting. All right, so what happens is the net force is 0, and if the net force is 0, then the net work done is 0. Okay, however, you know that if I let go of the spring after I compress it, by intuition you can understand that this spring is just going to expand and come back to this position. This work that is required to compress the spring is causing the energy to be stored as form of potential energy. Okay, when we talk about potential energy, we say that a mass, any particle that has mass, can have some potential energy due to the environment that is around it. Okay, so with potential energy, basically we say that it is an energy that is associated with the position and configuration of this particle or the mass. Okay, and some examples of potential energy are, just we talked about the wound of spring. You have a stretched elastic band that possesses some potential energy. Keep an object at certain height above the ground, then we say that it possesses some potential energy, right? So let's look at that example because that is the most familiar to you, the gravitational potential energy, right? So when an object of mass m, it follows any path and it moves a certain distance h from the ground, right? We say that there is some work done by this gravitational force, and the work done to lift the object is basically your mg times h, right? And this uh, potential energy that we say of an object at the earth's surface, we say that it only depends on the height h. Okay, and later on I think in the third unit we will be looking at the gravitational force, and we will be looking at Kepler's laws, and we will be looking at satellite motion in more detail, and there we will actually figure out where this force of gravity is coming from. Okay, so for now let's take it for granted that we know that the force of gravity is mg, and we say that at the surface of the earth we want to find what is the potential energy of an object. So all we have to do is we have to see the change in height of the object from any location. Okay, when we say potential, basically it is the capacity to do work, right? So for example, if you take an object and this is the earth's surface, and you move the object to certain height, let's say a distance y, and now the object of mass m is sitting at this location. So basically we say that it has some potential to do work, that if we let go of this object, then it will fall down because of the gravity, and this energy that it possesses is this mgy, okay, which is the force of gravity, mg times y, okay, which is the distance from this surface of the earth. Okay, now so let's take an example of an object that we have at some location y1. Okay, and we are using our hand and we are moving this object to another location y2 by moving a distance of h in the direction upwards. Okay, and what we are doing is we are moving at a constant speed. Okay, so when we are moving at a constant speed in the y direction, basically there is no acceleration, and our summation of all the forces in the y direction should be 0. Okay, so let's see what are the forces that are acting. You're moving the object by your hand, so you're applying some force, and that is your force external. So it is moving in the direction of the object, so that is positive sign. And your force of gravity that is acting on the object is on the opposite end. So we have to use a minus mg sign here. So that will be your equation of motion. Okay, that 0 is equal to F external minus mg. And the external work done by a person raising this object of mass m to some height h is basically your external force times your displacement, which is h, times the angle between it, and the angle is 0, so that just is 1. Okay, cos of 0 is just 1. So you get the value of the work that you have to do to raise the object to certain height h is basically your mgh, or essentially it is just the difference between y2 minus y1. Okay. Now what is important to understand that where is this y1 and where is this y2. Okay, so these reference points that we are choosing, that sometimes we choose the surface of the earth as the reference point, sometimes we might choose the table to be the reference point. So this is all arbitrary. Okay, since every time we are looking at what is the change in the potential energy, and that is just mg, which is basically constant for your case, and then it is just the difference between those two values of y. So you always get the difference between the two values. Okay, so if you look at the graph of, okay, how u changes with this location y, you can see that it is a straight line, right? This is just y equal to mx kind of equation. All right, so sometimes we choose the earth's surface as your reference point, so we can call it as point 0. And for example, we can say that at point a, the value of the distance is 0, and if I move an object from a to b, basically what I'm doing is I'm moving it by some distance y2 minus y1, right? And if this distance is h, then you get just your value of mgh. Okay, so this choice of this value of the origin is completely arbitrary, right? Because always you get the difference between y2 minus y1, right? So just to put that in other terms, suppose this distance difference is let's say 10, okay, and initial height was 10 and the final height was 20 meters, right? So when you take your potential energy gained when you move from y1 to y2, it will be mg times 10, right? So you get 10 mg in this case, okay. So again, this reference point we could have chosen as 0, okay, and then the difference of between y1 and y2 would be again 10, right? And even in this case, if you choose a as 0, then again you would get the same value as 10 mg as the potential energy gained, because the difference between y2 and y1 will always be the same, and that is your height of 10 meters, okay. Suppose you are moving an object from A to B. Okay, so you are doing the work. Okay, so when you are moving the object from A to B, basically what you're doing is you are doing some positive work. Okay, and when you're moving from A to B, you can see that the difference in the U values is positive, and that means that the gravity is doing negative work while you're doing positive work. Okay, and similarly, if you're going from A to C location, now you're going down in your potential value. So that is basically your potential value is lower here than what it started. So that means you are doing negative work. And in this case, because gravity is winning, so gravity is doing positive work. Okay. So in this scenario, what is again important to remember is the zero of your potential energy can be chosen anywhere as long as you're consistent with that choice in your problem. Okay. Of course, this potential energy, whatever is gained, basically can be converted into kinetic energy if the object is dropped, right? But like we were mentioning, it does not matter uh, where this reference point is, because always the gain in potential energy is mgy, and that is the amount of energy that will be converted into kinetic energy if the situation arises in our problem. Okay, and the another common example is that of a spring, and we can consider an ideal spring. And you should know this, that when we are saying an ideal spring, what it means is that it is characterized by some spring constant k. Okay, and this spring constant k measures the stiffness of the spring. The force that is exerted by the spring is given by this minus kx value. Okay, and in physics and in mechanics, this is known as the Hooke's law. Okay, but you should be aware that this is not actually a law, right? It is only true uh, till the point that you're considering that it is an ideal spring, right? Because beyond a certain point, there will be stretching in the spring that will not be recoverable. Okay, and in those circumstances, this law will not be valid. Okay, so to certain extent, to certain displacement, you can get this linear relationship of your spring, and that's characterized by this notion that it is an ideal spring. Okay, so when you're stretching a spring, again you're giving some potential energy into the spring, and this work done by the person in stretching the spring can be given by this expression 1/2 kx square. Okay, so when you provide this work to the spring, basically the spring gains some energy, and that is what we are calling as the elastic potential energy that the spring can store. Okay, and from the relaxed state, what you're doing is you're compressing or you're stretching the spring. Okay, and once you let go of the spring, this potential energy of the spring, suppose there is a mass attached, right, can be converted to the kinetic energy of the mass that is attached to the spring, right? So you probably have seen a lot of contraptions like guns or something that kids play, in which there is a spring loaded system, in which once you hit the trigger, the spring releases and it throws the mass to a certain distance. Okay, or an arrow to a certain distance. All right, so that is a very common example of providing potential energy to the system, and then the system is storing, and then it can release that potential energy and convert it into kinetic energy and cause motion. Okay, so when we consider an atom, right, we can imagine that the atoms are connected by springs. Okay, and later on, when you deal with complicated three-dimensional systems and solids, we can assume that the spring is basically getting stretched or getting compressed as the atoms are vibrating. So it has a huge implication in physics and in solving and understanding how materials behave. Okay, so I can give one more example. when we are concerned with temperature, and we try to understand how temperature plays into our characteristics of a three-dimensional system. Simply saying that suppose I have a solid and I want to raise the temperature of a solid by 10 degrees. Okay, so what kind of theory do I have to apply solve this problem? All right, and say that there is an atom, the atom is vibrating, and when you provide it some energy, and this energy is the thermal energy, then it can cause these atoms to vibrate in certain energy modes. So again, we'll be using this spring system. So let's take this case of the force. And interestingly, what happens in this case of the force of the spring is that the force is always negative, right? So it is always a restoring force. It's always a negative value of minus kx. Okay, so in this case where this spring is in its normal position, when unstretched position, there is no force acting, right? So however, if you stretch the spring by hand, and your displacement is a positive displacement, in that scenario what happens is this force is essentially a negative value. Okay, so although x is positive, the value of f is negative. Okay, because you know the k is just a spring constant. Okay, so it is a constant value, it's positive, it won't change. Okay, and interestingly, if the spring is compressed, then what happens is by your dimensional analysis, what you're doing is you're saying that x is going in the negative direction, so x is negative, and in this case now the force is going to be greater than 0 and positive. So again you get a term which is eventually negative. Okay, this is a case in which the spring is not stretched at all. Okay, so it is in the equilibrium condition, so there is no force acting on it, so there is no displacement, it is just sitting there. Okay, and if you plot this force versus x curve, which is the displacement, it will look like a straight line, and it will look like this with a negative slope, right? So again, this value of force at any point is just kx, and if you look at the area under this force versus displacement curve, you will see that this area is 1/2 times kx and times x square. So that is the amount of energy that is stored in your spring. Okay, and remember again, what you have to realize is this force is not a constant value. Okay, so previously when you are doing kinematics equations, you are using all the kinematics equations that were dealing with a constant acceleration. Okay, and the constant acceleration will only come when you have a constant force, right? But however, in the case of a spring, there is no constant force, the force varies, and the force varies with the displacement. Okay, so in those cases you cannot use kinematics equations to solve the problem. Okay, and you will have to use your work energy theorem, or you will have to use your potential energy functions to solve the problems. Okay, so you always have to keep that in mind, that the force in the spring is not constant. Okay, so again, let's take the example that this spring is in this equilibrium condition, and now somebody is pulling on the string, and you stretch the spring from some initial position x equal to 0 to some position x. Okay, and what will happen is because the initial velocity was 0 and your final velocity is again 0, because all you're doing is you're taking this mass and pulling on it and moving it to a second location. Okay, and in both the cases the initial velocity and the final velocity is 0. So from the work energy theorem, you know that the net work, which is the change in kinetic energy, will be 0. Okay, so let's see what are the forces acting on this system. This mass is sitting on a table, and it's a frictionless table. Okay, so the only force that is acting on this mass is the person who is stretching it, right? So it's basically the work that I am doing in stretching the spring, and then the force that is exerted by the spring, and so the work that is done by the spring. Okay, so that are the two works that are acting on this system. Okay, so let's see what is the work that I have to do to stretch this spring from 0 position to x. Okay, and we know that the formula is the force that I have to apply times dx. Okay, because it is a one-dimensional case. So the force that I have to apply will be opposite to the force that the spring is applying. So that is just kx value. So you can substitute that in this integral. So you have 0 to x integral of kx dx, and k, as we know, is spring constant, so it is a constant value. It will come out of the integral, and you are left with integral of x times dx, and that is nothing but x square by 2, right? So integral of x raised to n is just x raised to n plus 1 divided by n plus 1. Okay, so let me write that down. Integral of x raised to n dx is just x raised to n plus 1 divided by n plus 1. Okay, and that is all we are using here. Okay, so you get the work that I have to do is kx square by 2, right? And that is just the negative of the work that the spring has to do. Okay, because this work that I'm doing, what is it doing? It is basically providing some potential energy to the spring, right? And it is storing that energy in the spring. If I let go from this position, then this mass will start moving in the opposite direction because it will start swinging back and forth. Okay, so the potential energy that is stored in the spring is this value kx square by 2. Okay, and that's where this term comes from. Okay, so if you look at the potential energy function as to how the potential energy of the spring changes with respect to x, right? It is the x square term, so you get this parabola. If I am taking a mass and I am moving it, let's say from point A to point B. Okay, so these are correspondingly two positions on your x-axis, right? So those are the x-axis position. So let's say I'm moving a mass from position here, which is x of A, to position of x of B. Okay, thing is the work done by the spring will be positive. The potential energy function is going down. Okay, so it's just the same idea as gravity, you know. So potential energy is going down. You can see the value of u is going down. The corresponding value of u is here, corresponding to the A and B, and u is going down. That means the work done by the spring is positive. Okay, and another important thing to understand is that the force that is acting on the object is always opposite to the direction of the increasing potential energy. Okay, so in these cases, every time you move away from this equilibrium position, which is this position here, the force will always try to bring it back to the equilibrium position. Okay, so if you're displacing from B to A, the force is acting in the opposite direction. If you're going from here to here, then the force is again acting in the opposite direction. Okay, so the force is always opposite to the direction of the increasing potential energy. Okay, the force drives the mass towards the lower potential energy. So in terms of energy, if you look at what's happening in the system, is again this x equal to 0 is your position of your equilibrium. So here there is essentially no energy in the system. Okay, if you compress the spring, like in the situation B here, what you're doing is you're providing some potential energy into the system, and we just saw that the value is 1/2 kx square. Okay, so at this point, when you have compressed it by some position x and you have not let go, all you have done is you have provided some potential energy into the system, and that is your total energy of the system. Okay, so 100% of the energy is now potential energy in the system. Okay, and suppose now we let go of this mass, and this mass will start accelerating in this direction, right? So now then what you have is all the potential energy will get converted into kinetic energy of your system. Okay, so eventually you will see that you have 100% of kinetic energy, and that is your total energy of your mass m. Okay, so that's how the interplay of potential and kinetic energy is happening in your spring mass system. Okay, because both of the spring and pendulum are cases of your simple harmonic motion. Okay, so again, when the pendulum is oscillating back and forth between the end positions, so there is this restoring force that is making the pendulum go back to its equilibrium position. So very similar to your spring mass system. Okay, and again, your at the ends, basically you have the highest potential energy of your pendulum, and when it is in the middle position, you have the maximum kinetic energy in your pendulum. Okay, so a very similar system, and both of them are part of the simple harmonic motion. Okay, how we can simply use an experiment to measure this value of the spring constant, because we have been using this value of k for now, but we don't know how to characterize it. Okay, and you will be doing this in the lab as well. So all you have to do is, you have a mass, and this mass can be attached to a spring, and if you do that, what will happen is, this spring, which is fixed at one end, it has a hook on the other end, so that you can attach a mass to it. And once you do that, because of gravity, this there will be a force acting on this spring, and it will stretch the spring in the direction as it is shown here, and it will displace, let's say, by an amount d. Okay, so once it does that, it will attain an equilibrium situation in which this mg will essentially balance out this force f of s. Okay, and that is the force of the spring. Okay, and again, now it is not moving. Okay, so then your net force that you have in this situation, the sum is 0. Okay, and if you write down the equation, because the motion is in this direction, again you can write the net forces is mg minus your k times your displacement, which is the value d. Okay, and if you solve this, which is equating it to 0, from here you can find the value of k. Okay, if you divide by d, you will get k is equal to mg by d. Okay, so this is a simple and straightforward method to actually measure the spring constant of any spring. Okay, and you can take an example. Suppose the displacement happens by, let's say, a value of 2 centimeters, and this happens because of a mass of, let's say, 0.55 kilograms. Then k will just be your mass, which is 0.55 kilogram, times your value of g, which is 9.8, divided by your value of d, which will be 0.02 meters. And if you solve it, you will get the value of k as 270 newtons per meter. Okay, so this k essentially is used to characterize this springs, and it tells us whether the spring is very stiff spring, or it is a very flexible spring. So this is known as the static method of measurement. There is another method, that is the dynamic method, and we will be doing that dynamic method and static method in your second laboratory experiment. Okay.